Good morning, everybody. Welcome to Yaskawa America's training eCafe Express. My name is Nishant Unikrishnan. I'm an applications engineer with the Motion Division at Yaskawa America. Today's presentation is about the MP2000IC controllers titled Controller Parameters that Enhance Application Performance. Here's an overview of the MP2000IC system, motion system, with the controller, the servo pack, and the motor driving a load. I'd like to break this into two main components. The first one being the command processing and feedback between the controller and the servo pack, the first component here. And the second part of this motion process is the command and feedback between the servo pack and the motor. And in today's talk, I'd like to concentrate on the first of these two components, basically the command being sent from the controller into the servo pack to start motion. We basically want to make sure that all the commands that are sent from the controller down into the servo pack are optimized. So the programmer basically has to write his application program such that the commands that are sent into the servo pack are optimal commands. If these commands sent out from the controller into the servo pack are not smooth, no amount of tuning in the servo pack can help improve performance at the motor or at the load level. So basically we'll be looking at parameters that can be used to monitor the commands that are being sent and the feedback that the controller is getting back. So we'll be concentrating on this first, the top half of this scheme here. Some of the keys to performance are listed on this slide. I basically split out my motion into two categories. The first one on the left, synchronized motion, basically meaning gearing and camming, and the second one to the right is unsynchronized motion, which means your axis is independent. It is not dependent on another axis or any other signal. It is a discrete motion, for example, move absolutes or move relatives. Let's look at the first half here, synchronized motion, which involves two axes being synchronized to each other, either velocity or position. Some of the keys that will determine the accuracy and the precision of your application are filtered master data. So the master position or the master velocity that's coming in that needs to be used by the slave has to be filtered. Second one, and very important part, is communication delay that can happen in networked systems. The third one is feed-forward component. We'll talk about all these in detail later. And the fourth one is sub-interpolation in the servo pack itself. In the same way, for unsynchronized motion, you can make use of a moving average filter to smoothen the jerk in motion. We could use feed-forward components and also servo pack sub-interpolation. We'll look at all these components in detail and talk about these parameters in detail. Let us look at the first kind of motion, synchronized motion, and I'd like to talk about cams in particular, electronic cams in particular. This slide here gives a picture, a logic analyzer trace of a cam, a slave that is cammed to a master servo axis. Remember, it's cammed to a master servo axis. And the first plot that you see here, the parameter 1015, is the master's commanded position, the master servo's commanded position. And you can see the second plot is the master's commanded velocity. You can see how smooth that velocity profile looks. It's running at a constant velocity of 360 degrees in this example. And since this is a commanded velocity, it's pretty smooth. So any slave axis or any slave servo that you cam to this kind of a master profile is going to be a smooth profile, as you can expect, because the commanded position or the commanded velocity of the master is being used for the slave to synchronize to. And that basically results in a smooth velocity profile on the slave and a very smooth torque profile as well. Now, this is a case where the slave is cammed to a master servo. However, this is typically not how electronic cams are implemented on real machines. You seldom or very rarely cam a servo axis to another servo master axis. In real life, you basically have some external encoder that provides you the signal that acts as a master, and the servo slave is cammed to an external encoder signal. And this is a snapshot of what you can expect when you have an external encoder AB quadrature pulse signal coming in. The first plot there is the master encoder position. It looks smooth. The second plot you see in red is basically the encoder velocity that is calculated in the master based on the pulses. And this velocity you can see here, I'm hoping that I see a constant velocity of 360 units per second, but what I'm seeing in reality is a lot of spikes, a lot of hills and crests and valleys and all kinds of jagged data is coming through. And this is an example where I'm using an external encoder with a resolution of 8192 counts per rev, and you can see the velocity is going up and down. And when I try to cam my servo slave to this master position, my servo slave position looks smooth again. However, if you look at the velocity that my controller is commanding to the slave, it is indicative of how non-smooth it is. It's again, it is trying to reflect this velocity profile up here, because the servo slave is now trying to cam or synchronize with this master profile, master velocity profile. And what ends up is a torque profile that is jagged and spiky as well. So you can see here that with a very slow moving 360 degrees per second, 1 rev per second move itself, you're seeing pretty large torque spikes there. And when this application runs faster, and this is just an example of a smooth, of a straight line cam, and when this application runs faster, this is going to create more torque ripple, which can end up being audible noise. And usually when a servo generates noise, or if the torque curve looks ripply like this, people immediately start thinking, oh, I need to tune the servo slave. I need to tune my servo axis. But that may not be the solution, and that is not the solution, because if your master signal itself is not clean and filtered, then the slave is basically, even if you tune it tightly, it is basically trying to follow this rugged landscape of master position or master velocity. So in a sense, the slide or the picture that you see on the left is what you expect for your camming application. In a very optimal world, that's how you would be seeing it. But in reality, this is what you see with a lot of torque ripple in your slave axis. And the answer to that is not tuning. That's not the first thing that you need to try to attempt to do. So here are the tools that are available in the MP2000 IC series controller for filtering out your master data. As you go from left to right in this picture, you can see parameter 1007 is basically the position of the external encoder AB quadrature pulses coming in. The pulses are used to calculate the position of the external encoder, and 1007 is the raw position encoder data. 1008 is the modularized position for the external encoder. You can see the modularized figure here. 1008 is the parameter that shows you modularized position. 1009 gives you the velocity that is calculated from raw encoder pulses. And this is the first parameter that I'd like to talk about. 1306 in the controller is used, a moving average filter is used to calculate filtered master velocity, which is 1001. And that is essentially used to create a new profile for the master position. And this new profile for the master position is going to be smoother because it has been smoothened using a moving average filter on the velocity. And this, if this value is used as the master for camming or gearing, then you basically end up giving the slave axis a smoother command, and that'll be shown coming up pretty soon. Just a reminder, this block diagram, which I think is very useful in designing your application program, is available in the PLC Open Manual for MotionWorks IC 2.0. The 2.0 was just released last week, and this block diagram is available in the help. Now, these parameters are also available with older version of firmware starting 1.2.3, but you may not see it in older versions of the software help. This has been made available only in MotionWorks IEC 2.0, in the help in 2.0. Once again, just a smaller screenshot of what happens. Your raw encoder position, if that is used as your master to command or to gear or cam a slave, then you end up with a torque profile which is rough. It can sound rough. Your commanded velocity on the slave can be rough too. And what happens is when your torque profile is rough, you basically end up using more RMS torque, which ends up using ends up heating the motor up, and it's not totally good for the machine because you can end up with warnings and alarms because of higher heat being generated at the motor end. So a plot that looks like this with unfiltered master data, once it passes through 1306, which is a master filter, results in a profile that is much more smoother. And you can see here that once it is filtered, there is a slight change in the velocity profile for the slave that's commanded for the slave. And you can see there is a big difference in the torque ripple. And remember, I'm just running this at a low speed of 1 revolution per second. But even with that, with just a filter set in there, and the filter I used for this test was a 100 millisecond filter, I was able to see a big change in the torque that was used on the slave servo just by using a filter there. Now, one important aspect here is that 1306 is a moving average filter. So a very high number may make the master profile look extremely smooth. However, that'll introduce a lag in the master's position data coming into the controller. And therefore, you have to be careful. There is a trade-off. A high number on 1306 will introduce a bigger lag in the master data coming in because it's a moving average filter. A low value of 1306 will not filter out, will not make the profile smooth. So there has to be a trade-off. You have to come up with a number that's acceptable for the machine and for the architecture, for the application itself. Moving on to the second of parameters that I wanted to talk to you about. The second involves communication delays. Now, any network or any motion system that involves communication or a network that's used for communication has some kind of a communication delay built into it. And this right here, what you see is what you see on the x-axis. The units on the x-axis are Mechatrolink updates, or the updates that the controller uses to send data or commands into the servo pack, and the same updates are used to get updates from the servo pack into the controller. Here you can see a flow of data going back from the motor's encoder back into the controller application. This is the controller application scan, and this is where the data flows into the encoder. It goes up into the M-Link or Mechatrolink packet, goes into the motion kernel in the controller, and finally reaches the application where you read the actual position of the motor. You can see there is a delay of up to or greater than 2 Mechatrolink updates for the data from the encoder to reach the application. So if you read the actual position of a motor, you are essentially reading the position of the motor at this time and not at this time. So there you can see that there is at least 2 Mechatrolink scan worth of delay for data flowing up into the application. And if an external encoder is used, that data comes in here, and you can see that that also involves up to 2 Mechatrolink scans worth of delay. Now, if we look at the delay going the other way, let's say a command to ask the servo to move to a certain position was given at this time instant, that command takes time to flow down into the motor. And so basically this here again you can see that you can have up to 2 millisecond, 2 Mechatrolink scans worth of delay for a command to reach back, it'll go back through the servo pack into the motor. So if we consider all the delays in communication, basically you can see that up to 4 megacontrolling scans worth of lag between the master's actual position and the slave's actual position can happen if it is left uncompensated. The practical implications of this are seen on very high-speed registration-based machines where a master could have moved a significant distance in 1 megacontrolling scan. And this can lead to labels being misplaced in a labeling machine, or on rotary knife applications which have registration, the cut can be at a different location, because if the master is already moved and you're making decisions late, then your slave is commanded to work on a later position, which essentially leads to inappropriate cuts for rotary knives and inappropriate labels for labeling machines and so on. Now, here's an animation which basically talks about what I just, or which illustrates what I just talked about. This is a labeling application, a conveyor with an external encoder, a product which needs to be labeled, and this is an IEC controller here with a Sigma 5 amplifier attached to it, and this is a slave servo. The product, as it comes along, gets registered with the sensor. That data gets fed into the controller. By the time the data gets into the controller, the product is already moved ahead and it is at a new position. And then when the controller makes a decision to act on this data, the product has and the product has still further moved ahead. And by the time the controller gets, or the controller gives a command to the servo slave, the product is at a totally different location. The servo should have been commanded, so since the product was at position 4, the servo should have been commanded this position. If it was a cam, the product should have been commanded this position, but instead the product was, or the servo was commanded position corresponding to an older position on the master. And so the placement of the label can be wrong. So this is what happens when you have compensation with, or when you have delays that are not compensated for. In order to test these parameters or test the delay, the test setup that I used to generate the data, which we'll talk about, I used a controller with 2 servos on the Mechatronic network, and I commanded a move to axis 1. The pulses generated on this axis were used as my external encoder master that was fed into the counter circuit on a LIO card, and these signals were used as a master to gear to my slave axis. So in this test, basically I'm slaving my servo axis to an external encoder master, and the gearing ratio is 1-to-1 in this example that I'll be talking about. Here are the results of the first test. You can see that the command that's sent out from the controller into the first servo is this signal here. That's the commanded position for axis 1. It is not very important in this test. What is important are parameters 2 and 3, basically the external encoder position coming in and the commanded position going out. So 2 and 3 are the parameters that we're interested in. And the external encoder position, so you can see here that the axis 1 commanded position was 9.82. The external encoder position came back to be 9.72. So you can see right there that the external encoder is actually lagging behind the commanded position of axis 1. The external encoder is the actual value of axis 1, and you can see that that itself is lagging already. But this data that's coming in is the data that the controller gets. So that data also may be lagged, or maybe lagging a little bit. And then since we're doing a 1-to-1 gearing, that external encoder master position is what the slave gets commanded. So this is an example where there is absolutely no compensation either this way from the external encoder into the controller, and there's no compensation for the command going out from the controller into the slave axis. You can see here that this is the difference between what was commanded to axis 1 and what the slave is being commanded. Once the filter 1305 is used, 1305 is essentially the compensation filter, or the compensation term that is added to the external encoder data that is coming in. And this 1305 is the compensation that is added to the encoder pulses that are coming in. And what it essentially does is it reformats the master's commanded position, or the master's position, such that 1005 is basically now going to be different from 1008 in such that this has compensated terms in there. And you can see here the 1005 minus 1008 basically shows that compensation in position. And that difference can be seen when you take a look at the difference between the commanded position of axis 1 versus the commanded position of axis. If you take the error between the commanded position of the master axis and the slave axis, you can see the difference between these two. This on the left here is the uncompensated plot, and what you see on the right is the compensated plot where the 1305 scan compensation for external encoder position has been added. You can see that the difference between the master and the slave has already come down. An expanded view of that compensated position. You can see, if you remember from an earlier slide, the external encoder position that it was reporting was 9.72 e to the 7, but with the compensation that was used on the external encoder position, now that position is 9.76, and so you can see that the slave is now asked or commanded to 9.76 instead of 9.72, which was the number without compensation. So, in a sense, we looked at, in the last couple of slides, we looked at the external encoder compensation parameter, 1305, which was used to compensate for the delay in the external encoder signal going up and reaching the controller application program. We will now take a look at the second of the two compensations we'll look at here. This 1307 is a compensation that will be used to compensate for the delay in the command being sent out from the controller into the servo pack and to the motor shaft. And to do that, we basically have to take a look at this second block diagram. And if you look from left to right on this block diagram, basically this is where the controller makes a decision on what needs to be done. So if we are in synchronized motion, as we are right now, camming or gearing, the command that comes from the master encoder, this is the position command that comes from the master encoder, is basically used, and a compensation, 1307 compensation, is used so that the 2 M-link scans worth of compensation is added to that position, such that whatever the command goes into the camming or gearing block now has a compensated value. This is forward compensation from the controller into the servo pack, and that basically gets added onto the command that goes into the camming or gearing algorithm, and the slave data gets the final compensated position, which is shown in parameter 1015 or 1016. Once again, this block diagram will be available in MotionWorks IEC 2.0, the PLC Open toolbar, PLC Open help, online help in MotionWorks IEC 2.0. The effect of this forward compensation can be seen here. I basically tried to put these two block diagrams together, and the effect of 1305, which is the external encoder compensation, and 1307, which is a forward compensation on controller command going down into the servo pack, can be seen in this figure here. And you can see that the difference between axis 1 commanded position and the slave's commanded position has the error between those two has reduced further. The plot that you see on the left is the uncompensated plot, and the one that you see on the right is the plot with 1305 and 1307 being used in the application. Here's a more detailed plot of the compensations being applied. So if you remember from previous slides, the axis 1 commanded position was 9.82. That data is sent to the servo. The external encoder compensated position is 9.76, and this compensation is because of parameter 1305, and then once that was applied, we applied further compensation using parameter 1307 to compensate for delay in the controller sending a command out, and you can see that that compensation basically pushes the command position on the slave from 9.76 to 9.79. So this compensation is because of 1307, and this compensation was because of 1305. And here's an animation of how this compensation helps in our application. The product comes through in registration, the signal goes through, you have a scan compensation 1305 for the delay in this communication, and we also anticipate for compensation in the forward direction and make sure that 1307 basically takes care of that compensation, and so the slave essentially is ready for the position of the master. You can see here that when the product is at position 4, the slave position is also corresponding to that particular position on the table because of these two compensations already being incorporated. With Yaskawa's experience in registration-based motion, and with our experience with our hardware, we basically have set 1305 and 1307 to defaults of 2 Mechatrolink scans in the application. So if you're using an external encoder, you are going to see external encoder as a master in synchronized motion, either camming or gearing. You are going to see compensation of 2 Mechatrolink scans for 1305 and 2 Mechatrolink scans for 1307 by default. Now these are adjustable, so if you want to make adjustments based on your application, based on what you see on your application, you're free to do that, and you can use PLC Open function blocks like read parameter or write parameter to make adjustments to these compensation parameters. And this, I would like to say that this is basically like trap and skeet shooting. You know, if you have, if you need to basically aim forward to shoot a target, and how much you aim forward is basically based on the velocity. So for high velocity targets or high velocity applications, you basically have to look ahead because you know how much of hardware delays or network delays you have. So you're compensating for that and trying to make use of the velocity of the product to make compensations and hit the target position. Just to show how important this can be, on a labeling machine where a master encoder is running at 500 feet a minute, which is, you know, sort of a high-end or high-speed application, 500 feet a minute or 0.1 inches per millisecond, the error in position without compensation can be as large as 0.8 inches for a 2 millisecond Mechatrolink scan. Now 0.8 inches on a labeling machine can be a pretty substantial error. You know, imagine a label or a postage stamp being placed with an error of 0.8 inches. That's not acceptable on servo control machines. And with compensation or with scan compensation, you can eliminate this error without having to worry about even starting to worry about tuning. Because I understand that as soon as you see error in placement or error in product precision controlled by servos, people immediately start thinking about tuning. But this is an application, or this is an instance where you can, even before you start thinking of tuning, you can reduce your error so that you don't have to worry about tuning your application tightly or over tuning it and so on. I'd like to take, see if there are any questions on the chat window, see if there are any questions that everybody in the group would benefit from. If there are individual questions that you have individual, you will try to answer those questions individually. And right now I don't see any questions that are general in nature that everybody might benefit from, so let's move on. Now, all this time we've been talking about filters that probably would help synchronized motion, for example, gearing and camming. We were looking at how communication delays and scan compensation can be used to help in motion, and how master encoder data can be filtered out to get smoother slave profiles. Now moving on, let's move on to some filters that can be applied for both synchronized and unsynchronized motion. When I say unsynchronized motion, I mean discrete moves, like a move absolute or a move relative in the IEC platform. And here's a block diagram that shows you some of the filters that can be used to make your profile look smoother. 1016 is the command that the controller generates, which is sent out into the servo pack. Before it reaches the servo pack, you can apply a filter, the 1300 filter, which basically is a moving average filter that can be applied on the command. And what it does, and there is a time constant that you use for the moving average filter. The time constant is in parameter 1301. So if 1300 is enabled, it basically applies a moving average on the command that comes through. So if you have a trapezoidal move profile, you can apply 1300 filter and make that profile look like an S-curve acceleration and deceleration profile. Essentially, it's a moving average filter with 1301 as the time constant in there. The other parameter, moving on, the next parameter that I'd like to talk about is 1310, which is a velocity feed-forward component that the controller calculates, and the feed-forward component is directly fed into the velocity loop on the Sigma 5 servo pack. 1311 is the third of the filters that I'd like to talk about, and it's a switch which you can use to switch sub-interpolation inside the servo pack. So if 1311 is set to switch 1, it basically tries to make use of exponential sub-interpolation within the servo pack if the parameter is set in the servo pack is set appropriately, and if 1311 is switched to 2 in the controller, making use of parameter 812, whatever is set in parameter 812, a linear sub-interpolation can be executed in the motion profile that is sent into the position loop on the servo pack. We'll go through details on all three in the coming slides. The first one is the motion filter, or the S-curve filter that I just talked about. And in order to enable the motion filter, or the moving average filter 1300, it needs to be set in the hardware configuration or the configuration tool in the software. And once it is enabled, the time constant can be changed, or it can also be disabled through the program. But the first time it will have to be enabled in the configuration table to be true. Once it's set in the configuration, it can later on be enabled or disabled, or time constant can be changed through MC read parameter or MC write parameter. This is how the filter 1300 affects your commanded velocity, and I'm showing commanded velocity because this is where the effect of this filter can be seen very clearly. The commanded velocity basically takes an S-curve shape once it goes through the filter, if the filter is enabled, and this does not reduce the accuracy. So for a point-to-point motion profile, if the filter is set, it does not reduce or does not increase the error in your final position. All it does is introduces a delay worth the time constant that you set in there. You will not. So if you're going from point A to point B, you're commanding it to go from point A to point B. You don't have to worry that it does not reach point B or it overshoots point B. It basically does point A to point B, except that now there's a delay of 0.1 second if that's what's set in 1301. Moving on, the velocity feed forward component, or the velocity feed forward term in the controller, is 1310. And 1310 is by default set to be true in the controller. And 1310 is very useful for point-to-point applications for both synchronized or unsynchronized motion. And this is essentially, or this is very useful if you want the position error or dynamic position error to be reduced or close to zero, as you can see in the figure. The figure on the left basically is a plot. The yellow that you see here is the position error, and the green, which is under this purple line, is the commanded velocity, and the purple line is the feedback velocity. You can see that the feedback tracks the commanded very closely, fairly closely, but the position error that you see here is because of the lag between the commanded velocity and the feedback velocity. Now, if that lag is not acceptable, the only application I can think of where a lag is not good is when you have contouring applications where you want the feedback to be as close to the command as possible. Only in contouring applications would I think that's very important. For applications that are point-to-point, let's say you're worried only about your starting point and your end point, this lag that you see here is not important. You can live with the lag. And actually this lag is okay because it reduces the overall torque reference of the servo system. But let's say you do not want that lag and you want to get rid of that lag. This controller parameter 1310, which is on by default, comes handy because you can see here once that is set, the same profile now runs without position error, or the maximum position error you get here is about 6,000 reference units. So you can see that the steady state position error has been totally taken off, and it's totally eliminated with 1310 turned on. An important thing to note here is that this feed-forward compensation term calculated in the controller is done at the Mechatrolink update rate, which is 2 milliseconds. And the servo pack position loop update is much faster. It's about 125 microseconds. So when this feed-forward is applied into the servo pack, or when it is given into the servo pack, this can be quite a harsh or quite a big jump in feed-forward velocity. So care needs to be taken when you apply this parameter in your application. I would not recommend this parameter be used on applications that have very high changes or very high acceleration in the profile, because if you have high acceleration, that means your velocity is changing rapidly, and if it is being sampled at every 2 milliseconds, you might be feeding forward very high velocity terms. So it might basically end up giving more torque than that's required, and you might end up with overshoots on your system. So you have to be careful when you choose or decide to use or not use 1310. Once again, 1310 is not recommended on applications that have very high changes in velocity in very short periods of time, or if your acceleration or deceleration is very high, we would recommend not using 1310 or turning off 1310 to reduce the torque on your servo. Here's a comparison where 1310 was turned on, and we're comparing it with another feed-forward component that is available in the servo pack, which is parameter PN109. So if 1310 is turned on, you can see here in the first of these two plots, you can see that the green here is the commanded velocity and the yellow is the feedback velocity. You can see that if you compare between these two plots, you can see that the yellow tracks the green much more closely in the first one where 1310 is turned on, and this is because of the high velocity feed forward being used here. You know, it's a strong velocity feed forward, but what it does to torque is it generates greater torque, and over multiple cycles your RMS torque can be higher. And this again is from a very high speed application, a real machine. And you can see here when 1310 was turned off and the servo pack speed feed forward term PN109 was turned on 100%, you can see that the performance is pretty good. However, you know, it may not be as closely matching the performance on 1310, but the torque requirement with this profile or with this parameter is lower. So RMS torque can be reduced, heat on the motor can be reduced, and so on. The reason is that the speed feed forward component in the servo pack, PN109, is updated at the servo pack interval. So you're getting faster updates on it, so it is not as harsh. The feed forward that is calculated with this term is not as harsh as 1310 is. Again, there's a difference between these two. 1310 is the controller parameter. PN109 is a servo pack parameter. This PN109 gets updated at the servo pack update interval, and 1310 gets updated at the controller or Mechatrolink update interval. The next term I'd like to talk about is sub-interpolation in the servo pack, and this is a very important parameter as far as we're concerned, because this helps in reducing the torque requirements on the application by a great extent. And this is important for both synchronized as well as unsynchronized motions, and we would recommend setting these parameters for all applications irrespective of performance requirements or accuracy or precision. We would recommend working with these parameters here. 1311 is, like I said, it enables servo pack sub-interpolation. The plot that you see on the left here is without servo pack sub-interpolation being enabled, and the plot that you see on the right is with servo pack sub-interpolation enabled. To give you a little background, the controller sends commands to the servo pack every Mechatrolink cycle, in the case of Mechatrolink type amplifiers, and every and it is a DP RAM update for the 2600 type controller, which uses option style servo packs. Now, the Mechatrolink cycle by default is set to be 2 milliseconds, and the DP RAM update also is set to be a default of 2 milliseconds. Now, in servo pack update land, that is very, very long. The servo pack basically updates much faster than that. So the servo pack has to wait for multiple of its cycles to get a new update from the controller. Now, so when the servo pack looks at this, and remember these are sigma win plots that are taken at high resolution, when the servo pack looks at the controller or waits for the controller commands to come through, the servo pack, if the sub-interpolation is not included or not enabled, the servo pack sees step changes in controller commands coming through. And so every time a step change happens in its command, the servo pack essentially has to send out a large change in the commanded torque, or it uses a large change in commanded torque. As you can see here, every step it basically commands a large change in the position that it needs to jump through. So it's almost like it's going through multiple steps, and that can be harsh on the torque requirements for the servo pack. Now, if you let these sub-interpolation parameters enabled, essentially what it does is it smoothens out the command that the servo pack gets, as you can see here in the plot to the right. And that basically helps in smoothing out the torque requirements on the servo. So you don't have as many jumps in servo, in torque requirements on this plot to the right, just because the sub-interpolation on the servo pack using parameter 812 and controller parameter 1311 were enabled. The parameter 812 or 811, depending on what kind of sub-interpolation is required, has to be set to the same number as the Mechatrolink or DP RAM update in the between the controller and the servo pack. Here's an example of a real application where we tried out. This was a camming application where we tried out sub-interpolation. This was a high-speed application that was running at 20 hertz. And this is an example of PN1311, the switch set to use linear sub-interpolation. And this was the same profile where exponential sub-interpolation was used. 1311 set to 1 uses PN811, and that uses exponential sub-interpolation. You can see how the profile looks slightly different with exponential sub-interpolation in this case, as opposed to linear sub-interpolation here. So, in summary, we looked at a moving average filter. We looked at a velocity feed forward that can be used to reduce your dynamic position error. And we also looked at the servo pack sub-interpolation 1311, which is a switch which will have to be used in conjunction with servo pack parameters PN811 or PN812 to basically make sure that you have sub-interpolation between these step commands that are coming from the controller. For MP2600 IEC controllers with Sigma 5 option style amplifiers, The first two parameters work in the same way, except the switch parameter 1311 is non-existent on the 2600 IEC controllers. So instead of using a switch, we basically make sure that a different set of parameters in the servo pack are used for this kind of filtering. Instead of 812, parameter 812 in the servo pack, we use parameter 217 for moving average or linear sub-interpolation, and parameter 216 for exponential sub-interpolation. You need to use only one of these two. You don't have to use both. By default, these are set to be 0. You'll have to set them to be equal to the DP RAM update for these sub-interpolation values to take effect. In summary, we looked at the synchronized motion profiles where the master data could be filtered using parameter 1306, and then communication delay or network communication delay could be compensated for using 1305 and 1307. We looked at the feed-forward component 1310. Again, caution, care needs to be used for the use of 1310, which is not very highly recommended for profiles where velocities change rapidly over motion scans. We also looked at sub-interpolation at the servo pack level, which is parameter 1311. Here's an example of customers who benefited from using the sub-interpolation in the servo pack or parameter 1311. This was a camming application where they were using 4 millisecond mechatrolink updates. Their calculated RMS torque when they were sizing the system came to about 66%. And when they ran tests, they were seeing that the RMS torque was all the way up to 96%. Ended up overheating the encoder. They were getting encoder overheat alarms, and they had already started designing heat sinks when they contacted Yaskawa. And on looking at their torque profile, we suggested using sub-interpolation of 4 milliseconds, which immediately reduced their torque to 67, RMS torque to 67%. And you can see here how close this 67% RMS torque while the motor was running is close to what they had calculated. And their machine ended up being much more smooth sounding and silent. So reducing RMS torque essentially reduces motor heat in the whole machine. The second customer example I'd like to show was a high-speed indexer, which needed to get a digital input in command motion immediately and settle to within 0.36 degrees, so that within 20 milliseconds for the next input to come through and the next motion to start. And the challenges were basically tuning again to get a fast reaction and to settle within very short periods of time without making the motor too hot, without having high RMS torques. And after our tests, we were able to see that using 1311 and setting the parameter, the sub-interpolation parameter for linear interpolation, we were able to settle down within 18.5 milliseconds. The requirement was 20 milliseconds, and by using linear sub-interpolation, we were able to reduce the whole cycle time to 18.5 milliseconds. And you can see here how the torque profile also gets smoothened out because of linear interpolation being used in the application. One important thing to note here is that and this was an MP 2600 IEC application, and you're probably wondering why you see step profiles for the commanded velocity on this application. This is because on the 2600 IEC controller, the position profile that you see on the Sigma Wind software is taken before PN217 acts on it. So this profile that you see, the green profile with the step on it, is taken, or that data is taken before PN217 acts on it, which is why you can see the actual position is smoother than the step command position. If PN217 were not used, the actual position would have mirrored what you see on the green commanded position. But you can see here that the actual position is smoother now because that command that this is getting from is after PN217 acted, which is smoothened, which is a smoother version of this step command. So on the 2600, you will not be able to see the smooth command. If you plot position reference speed, you'll be able to see only the step command. Whereas on the 2300 SIEC or the 2310 SIEC controllers with Mechatrolink type amplifiers, you will be able to see the smooth command position based on the smoothing set in parameters 811 and 812. So in short, servo pack sub-interpolation was critical in bringing down the RMS torque and preventing the encoder overheating. A couple of other parameters, we're running short in time, but I'd just like to mention a couple of other parameters that might be helpful in certain applications. Some of you might have used them, some of you might not have come across these parameters because these were added as newer firmware versions came out. The first one is high-speed output that can be fired at a hardware level based on external encoder position. So as you can see here from the picture, a high-speed output on, if you're using the IEC series controllers, this can be used on LIO1, LIO2, LIO6, and also on the 2600 output. And this output can be used for triggering a digital output that can be triggered within 13 microseconds of an external encoder reaching a specific position. Now, where can this be used? This can be used for stations or downstream stations, for example, inspection and validation stations downstream from a machine that is controlled by an IEC controller. Let's say it's a labeling machine, for instance. The product that comes through gets registered and it gets labeled, and let's say we need to trigger a camera to capture the label position for inspection purposes. We basically can trigger that camera based off a digital input on the IEC controller if the position between this registration sensor and the camera is known. The external encoder position can be used to trigger the high-speed output to ask the camera to take a snapshot when the product reaches that position. So this is one example of use of a high-speed output from the IEC controller. The second of the two parameters that I wanted to talk about lastly was the option monitor read that has been made available, and it is available for firmware revisions 1.2.3 and above. Parameter 1312 can be used to read option monitors that are set in the servo pack. So in the servo pack, parameter 825 for Mechatrolink type servo packs, parameter 825 can take any of these values to monitor any of these parameters in the servo pack. And worthy of mention here are two important ones. One of them is the accumulated load ratio, or the RMS torque that Naxos uses. So if 825 parameter 825 is stored with 19, it basically uses, or it basically collects the RMS load ratio or the RMS torque from the servo pack, and then that can be used to be that can be read back into the controller application, which can be passed on to an HMI using parameter 1312 in the controller. What you see here, if this snippet is run through in the program application, you basically would read the RMS torque here. Of equal importance, or another important term that can be read back from the servo pack is the regenerative load ratio if region resistor packs are used in the application. Thanks for joining us, and hope this was beneficial. Hope this helped in answering some questions, clearing some concerns, or will probably help you in designing your applications better. Thank you.